this video, we're going to be talking about what a capacitor is, what are the factors that affect capacitance, how it produces an electrical current, and then also how capacitance changes in series and parallel. Now, the first thing we're going to take a look at is the anatomy of a capacitor. We have two conducting plates. And those two conductors are separated by this yellow material, which is called a dielectric. Now, a dielectric is basically an insulated material that allows those two conductors to be separated and not have a current run between them. So basically what happens is we have a certain voltage source over here that provides some kind of delta V. And when it's hooked up to the conductor, it's going to allow the flow of charges to move. Now, when it does that in the counterclockwise direction, the negatives are going to start to collect on one end, and then the other end is going to have a lack of electrons, causing it to be positive. So then we'll have a positive and a negative end, which will produce an electric field that goes from the top to the bottom based on how I drew this. Now, once those plates get all charged up, at a certain point, they can't hold enough charge, and they're just going to reach their maximum capacity of how much charge it holds. At that point, nothing's going to happen, and there won't be any current in the circuit. At that point, you would actually replace something like this battery with a light bulb, and once you place a light bulb in there and remove that voltage source, those electrons are going to flow back in the opposite direction until each of the plates are electrically neutral, and it's going to provide you with some electrical current for some period of time. Now, with this formula, Q equals IT, charge equals current times time, what it can do is either provide a lot of current for a very short burst of time, or can provide a little bit of current and then extend that amount of time. This is all dependent on the circuit and what your objective is for that particular electrical component. Now, there's three factors that affect the capacitance of the capacitor, and one of them is the area. So obviously, if you have a larger area for the conductors, it's able to hold more charge. The second thing is the distance, which is the separation between these two conductive plates. And the last one is the permittivity. And I think that's how you spell permittivity. That looks like it has too many T's, but I think that's correct. So that's the permittivity of the dielectric. So basically what that means is the degree to which this dielectric polarizes its materials. Okay, so what does that mean? That means that all of the molecules, or excuse me, all of the atoms inside of this yellow area are normally randomly turned and scattered all over the place where there's no uniform electric field of any sort. Now, when it eventually feels this red electric field from these two oppositely charged conducting plates, it causes the atoms to polarize by making the electrons lean towards that positive plate. Now, what those polarized atoms will do is counteract that electric field, causing the electric field to become weaker between those two conductive plates. What that does, it actually decreases the electric field between those two conductive plates. And if you decrease the electric field, what it does is it increases the ability for the conductors to hold more charge if there is a weaker electric field between them. So that's a positive thing in having a capacitor hold the maximum amount of charge. So now let's take a look at what's going on with a capacitor in a series and a capacitor in a parallel circuit. Basically what happens is this. These two capacitors here would have the positive and the positive and negative plates as shown from our initial diagram over here. Now what happens is when these two capacitors are combined, there is no net charge in the middle here. So it's basically kind of acting like one large capacitor. So we have a positive end here and a negative end here, but now we've increased the distance between them. If we have increased the distance, that increases this D right here, which is in the denominator of our formula because it's an inverse relationship, therefore causing the overall capacitance to decrease. So when you find the total capacitance in a series, you have to add them up as inverses. So your series rule is 1 over CT equals 1 over C1 plus 1 over C2, and then so on if there's 3, 4, or 5 capacitors. Now for our capacitors in parallel, what happens is, say for example that they're maybe powering up some kind of bulb over here, and they have a positive and negatively charged plate, as do all capacitors once they've become charged up from some kind of voltage source. Now what they do is it sort of, again, acts like one large capacitor. It's like one large positive over here, and it's almost like one large negative over here. And then it's able to push the electrons clockwise and then collectively power that light bulb. So now what you've done is you've basically increased the area, and the area is directly proportional to the capacitance. So once you've increased the area and you've allowed more charge to be built up on those plates, then you have increased your capacitance. So for a parallel, you would sum up the capacitance of each of your capacitors. So I hope that was helpful to you in understanding the anatomy of a capacitor, the factors that affect it, and then also how capacitors in a series and parallel work with one another to decrease or increase the overall capacitance. Thank you for watching and listening.